let's consider a distribution of charges, Q1, Q2, etc., Q3, such that the total charge of this distribution, so I'm going to sum over all the charges, j goes from 1 to n, is 0. So it's a neutral distribution of charges. And I want to define a new quantity called the dipole moment, which characterizes how those charges are distributed in space. And our definition of the dipole moment, P, will be as follows. It will be a sum over all the charges, and it will be a product of the charge times a vector rj. Now, this vector rj we'll define in the following way. We'll choose an origin, and we'll define a vector from the origin to where the charge is located. That is R1. Let's indicate the jth charge over here, and that's the vector rj. And so this is called the dipole moment. It's a vector, and we want to be able to calculate that for a number of given distributions. Now, there's a number of important things to look at this. When we see that we've chosen an origin and the quantity rj seems to depend on the location of the origin, then does this dipole moment depend on our choice of origin? And the answer is no. This is because the total charge of the distribution is 0, this quantity is independent of the choice of the origin. And we'll show that explicitly in a moment. The second thing that we should think about is, what is this meaning of multiplying charge by some vector location? And I think you've seen that before when we talked about the center of mass. And when we define the center of mass vector, RCM, with respect to some origin, it was the sum j goes from 1 to n of a physical quantity mass, mj, notice charge, times the location of that mass with respect to our choice of origin. Now, we divided it by the sum of the masses, j goes from 1 to n. And this defined the center of mass of a distribution of masses. Well, the dipole moment sort of looks like that. In the same thing, we're weighting each charge by its position vector with respect to the origin, and it's a vector quantity. But notice that we're not dividing by the total mass. And that should make sense to you, because remember, charge can be positive or negative. The total distribution of this charge distribution is 0, and so we would be dividing this weighted sum by 0, and that wouldn't make sense. And that's the difference between the center of mass and the dipole moment. And now let's calculate explicitly the dipole moment for a few distributions of charge, and also remind ourselves why it's independent of the origin.